Okay, hi everyone. Today we are going to be doing this example of comparing fractional crystallization using different thermodynamic models. So if you go to the PET Thermo Tools, read the docs page, and you scroll down, it's this example here. So as normal, you can just download it here, and I am going to open it in VS Code. Now some of these calculations take a bit of time, and my laptop is very slow when it's running recording the screen. So we're just going to pretend I'm running it as we go, but to save you all time. So just a reminder, if you want to use this, you have to follow the installation guide because we are going to be using both Alpha MELTS and MAGEmin today. So make sure that you go and read those installation things and watch the associated videos. So the first thing we're doing is we're just loading in where I have put my Alpha MELTS installation. Something to be aware of is you probably want to update PET Thermo Tools. Matt pushed a big change recently. So basically you would run your pip install upgrade, and then also once you've upgraded PET Thermo Tools, you also want to upgrade this MAGEmin calc. So you would just uncomment this and run it. And that's a general rule. Anytime you upgrade PET Thermo Tools, you're going to want to upgrade that MAGEmin calc as well. So here I'm operating on version 0.3.0. You need to be at least this version or higher because this has the ability to compare the masses between the different models that we're going to be using here. And just as a reminder, if you're running on Mac, you're going to want to run this cell twice. That will suppress all those annoying print outputs from MELTS. In this case, you can run this if you're on Windows. It's not going to do anything because you're not going to enter this if statement. Okay, so basically here we are going to load the Fernandina data like where we did in that example where we were choosing a single model. This is basically some melt inclusion and some matrix glass data. And what we're going to do here is basically sort the melt inclusion values so that they're ascending. So we have the highest MgO here, and we are going to choose the highest MgO melt inclusion as our starting composition. And that's what we're setting up here. We're then going to run isobaric crystallization models using the different thermodynamic models. So you can see here we are running using MELTS v1.2.0. And we are running at 500 and 3000 bars. Again, you could run at more pressures, it's just going to take longer. As before, we're setting our start temperature, our temperature step, our buffer, so here FMQ-1, and in this case we are fractionating both solids and fluids, and we are labeling the outputs based on pressure because that is what we have run two different calculations for. So my laptop, that takes about 25 seconds, again my laptop is incredibly slow. We're also going to run it with pMELTS, with MELT 1.0.2, and then this is the cell where we're going to run with MAGEmin. So this is using the green 2025 model, which updated at the pyroxene model. This one takes a bit longer. It does on my laptop anyway. It takes about 30 seconds to initiate Julia, so be a bit more patient with this one. But all of these will run. You can go make yourself a cup of tea, and then you can look at the results. Okay, so the first thing that we're going to do is we're going to compare the liquid major element chemistry for these. So what we're basically doing here is just a reminder for those who maybe haven't watched the other videos recently. This isobaric crystal 120, this is the output from that MELT calculation using version 1.2.0, and it has a variety of keys. This is a dictionary. So remember there are keys for each pressure you've run at, so we might want to start with look at the 500 bar pressure. This is going to return another dictionary, which also has keys. So in this case, you could look at the composition of liquid 1, for example. And then each step down here, this is a step in your model, and this is the composition of liquid 1 from MELTS 1.2.0 at 500 bars. Equally, you can use that all data frame that has things like your temperature, your pressure, your mass of the system. And then you can also, what we're going to be looking at today is the mass data frame. So this is the mass in grams, so the system is 100 grams. And you can see this is the mass of liquid, the mass of the olivine, the mass of the fluid, and then the cumulative mass of these phases as well. So basically if you add up these two numbers, this is the mass of olivine that forms in step 1 in the model. This is the mass of olivine that forms in step 2. And it checks out that the cumulative sum is basically those two numbers added together. Okay, so what are we plotting here? We're setting up two subplots, and we are plotting at 500 bars the results of 1.2.0, 1.0.2 pMELTS, and that MAGEmin model green for MgO versus FeO total. We're then going to do the same on the same plot for that 3000 bars model. We're going to do that with a dotted line rather than a solid line. And then we're going to do the same thing for aluminum versus magnesium. That's what these two code blocks are doing. We're then going to overlay the melt inclusion and the glass data. So we can just run that. And there's a couple of things you can see here. So different colours are different models. So red is 1.2.0, blue is PMELTS. You can see that in general, the difference between the two different thermodynamic models is more different than the difference in pressure. So for example, you can see MELTS 1.2.0 at 0.5 kilobars or 500 bars, it's that solid line. And then at 3 kilobars or 3000 bars, it's that dotted line. So that's a really, really subtle difference compared to the difference between, say, green and PMELTS. So this is worth knowing that if you're like iterating on a pressure, you're also going to want to check like, okay, so that might be the right pressure, but do all the models agree here? You can also see pretty drastic in terms of the paths that some of these models are taking. You can see that the difference between the 0.5 kilobars and the 3 kilobars is far more different in this aluminum space. So it does depend. It was just really this iron magnesium space where you see that big difference between the models. Okay, so what if we want to actually look at maybe why there are these differences? We might want to look at what phases these different models are stabilizing. So here, this is basically taking that output from the green model, looking at 500 bars, looking at this mass data frame, and then seeing what the columns are. So we can see that MAGEMin has stabilized clinopyroxene, olivine, a feldspar, and a liquid. In contrast, MELTS has stabilized olivine, a liquid, a fluid, a clinopyroxene, a second clinopyroxene. This is something worth worrying about. Sometimes MELTS and MAGEMin will put two clinopyroxenes. That's why they're labelled clinopyroxene 1 and clinopyroxene 2, and a plagioclase. So again, just worth noting that when you're comparing these outputs, MAGEMin does call it feldspar, and MELTS does split it into plagioclase and potassium feldspar. So when you're plotting, you just have to account for the fact that there are those options. So what am I doing here? I'm going to loop through all of the models at 500 bars. So you can see I've just set up this list of the models for 500 bars and I've given them each a label. I've then allocated them a colour for each of them. And then what I'm going to do is I'm going to choose an x-axis for my plot. So here I'm going to plot the magnesium content of the liquid. And then I'm basically going through and seeing, is there an olivine cumulative sum column? If there is, get the cumulative sum of olivine, otherwise set it as 0, and then plot the x-axis, so in this case the MgO in the liquid, versus the cumulative sum of olivine. I'm then doing this for feldspar, both accounting for the fact that the column might be called plagioclase or it might be called feldspar in the different models and looping through. And then doing the same for the clinopyroxene 1 and the clinopyroxene 2, showing that on the same plot. So we can basically look at this. So you can see that all the models are actually predicting pretty similar amounts of olivine, which makes sense, why then their iron and magnesium systematics are reasonably similar. You can see that what is really different is the onset of plagioclase crystallization. So you can see that MAGEMin, or that green model, predicts that plagioclase is beginning to fractionate at about 8.5, 8.7 weight percent magnesium, whereas PMELTS, for example, is only doing that at 7.5 weight percent magnesium. So we can go up. We can see that difference. So here we're looking at the solid line. So you can see MAGEMin starts fractionating plagioclase much earlier. So you get that big drop in aluminum as the plagioclase comes on, and that's, got a lot of aluminum in it. And then you can see for PMELTS that plag stabilizes much later. So that aluminum drop is much more delayed. So it ends up going up. And that's accounting for the much bigger difference in these models than in, say, these models. What else have we got going on? We can see that PMELTS doesn't stabilize clinopyroxene, whereas 1.2.0, 1.0.2 and green does. They actually predict reasonably similar amounts of clinopyroxene and reasonably similar offsets. And then you can just see a small amount of CPX2 coming in for both of these. So this would be this at 500 bars. We might want to do it at 3000 bars as well. So what we could do is we could just quickly, again, you could use a find and replace for this as well. Do this at 3000 bars. And we're also going to want to check what phases we get at 3000 bars, just so we have some idea what to expect. So I'm just going to copy this and have a look. So just change this to 3000. So in this case, it seems like it's pretty much the same. The only difference is we are getting this rhombohedral oxide, so you could add that to the plot. For now, I'm just going to see what this looks like without adding that. Okay, so what you see is that at 3,000 bars, again, you see this difference in plagioclase, but you also see this big difference in clinopyroxene. So basically, if we remember at 500 bars, PMELTS barely stabilised any CPX, whereas here it's starting to put it in at about 6 to 8%. So say we wanted to look at the rhombohedral oxides, we might want to check again just what we're seeing in MAGEMin as well. Let's just take this down, see what phases we have in MAGEMin. So there we can see it's not putting a spinel phase in. So here I might just want to add a fourth plot. It's going to get quite skinny, but we can deal with that. And then we're going to basically change this and just add one at the bottom for rhombohedral oxides. Rhombohedral oxide. That is going to be plotting on AX4. And we'll just grab what it's called. One sec. So here it is, this rhomb oxide 1, so we can just copy and paste that in. So we're replacing this for olivine. Let's just call this R1. Okay, let's see if that works. Yeah, so there you can see we need a tight label because we've ended up squishing our plots together too much. There we go. And let's just add a y-axis to this. So amount of rhomb oxide. So you can see you start to form these rhombohedral oxides relatively late in the fractionation path. We can just go up. And you'd probably be able to see that if you looked at some of the kinks in some of the other elements here. So in general, a great way to interpret the different paths that you're taking through major element space is to look at the amount of different phases that you're forming, and then knowing that, like, you know, a lot of aluminum is going in the plage, etc. And these are great ways to get students thinking about different phase assemblages as well. Okay, let's talk a little bit about that CPX2, because this is something to be aware of. So sometimes you will stabilise a CPX1 and a CPX2. Sometimes that CPX2 will be high calcium, sometimes it will be low calcium. It's best to just inspect them to see what you've got going on. So here we're going to import a thermobar to be able to plot ternary plots, and import this ternary package as well. If you don't have these, you'll need to pip install them. And what we're doing here is we're basically taking the CPX that produced at 500 bars, and we are calculating the ternary points using thermobar. We're then going to do the same for clinopyroxene 2. The only thing you need to do before you put it into thermobar is remove the CPX2 from the columns and replace it with CPX, just because otherwise thermobar doesn't know how to handle it. And then we're going to plot this. So you can basically see that most of the CPX that this particular model, this was MELTS 1.2.0 at 500 bars, produced it nicely within this clinopyroxene field, but one CPX1 and one CPX2 ended up kind of like towards that wolastanite end member. So again, there's no guarantee that CPX1 or CPX2 is going to be the weird composition, just worth knowing that these are some of the things that stabilised. As well as thinking about when different phases come on the liquidus, which is totally going to control your liquid line of descent, you might also want to think about the chemistry of the phases that are coming on the liquidus. So if one model puts a lot more aluminum into CPX, that's going to affect your path through aluminum space as you do your fractional crystallization. So here we're doing the same thing as before. We are looping through all 4 models at 500 bars. We've set the same colours as before. Now we're going to plot them on a ternary diagram to start with, and basically just plotting the CPX1s and the CPX2s for every model. And you can see roughly in this N-type ferrocellulite wolastanite space, they are reasonably similar. You do notice that the MAGEMin green calculations are a bit lower. So at this point, it might be that visualising this in ternary space isn't the best solution. So we might want to think of it in terms of clinopyroxene components and clinopyroxene oxides. So again, using that same code, we're now looping through a 6-part figure. And we are using the thermobar calculate clinopyroxene components function. This is going to calculate our jadeite and stuff. It's not actually used in this example except to calculate the Mg number of the CPX. And this is calculating it assuming that all Fe is Fe2. So first we're going to plot aluminum, sodium, chromium, calcium, titanium and silica against the magnesium number of the CPX. And this is when it becomes quite interesting to see the differences. So you can see MELTS 1.2 and MELTS 1.0.2 have way higher aluminum in their CPX than green. It's worth noting PMELTS didn't stabilise any CPX in this model, so that's why it doesn't appear on these plots. In contrast, you see that green stabilises way more sodium in the CPX. And this is going to be important if you're trying to do like barometry of MELTS calculations. This is really going to affect your jadeite, and you'll see that in a minute because that aluminum and the sodium are so key to calculating that jadeite. None of the models have chromium. It's going to affect your ability to calculate some of those other components. And then your calcium, you can see that MAGEMin puts way less calcium in, which is why it was plotting low on that ternary diagram. And MAGEMin puts way more silica in. Titanium, again, MELTS has a bit more titanium than MAGEMin. So if we think in terms of the clinopyroxene components, same code, we're just now plotting jadeite. We're plotting the cation sum of CPX just to check they look reasonable. The CATS component and also the amount of Fe3 that it puts in. Again, this is kind of a function of those other cations. This is what you see. So you see the jadeite is almost a factor of 2 difference. The cation sums, these are all like within a reasonable range. Most people that filter cation sums would filter within 0.02. So actually all of these would be like stoichiometrically reasonable. And yet they do have big differences in these CPX components and the CPX Fe3. So this is important if you're using thermodynamic outputs to compare these kind of CPX components like jadeite to your natural samples to invoke things about your PTX conditions. You really want to make sure that the thermodynamic model you're using is doing a good job of this. The best way to do that would be to find some suitable experiments for the bulk composition and PTX conditions of your system and just see, like, you know, which model does a better job of reproducing the experimental CPX that like your system. That model is probably the more reliable one to do these kind of comparisons. So it might be that none of the models do a good job, in which case this wouldn't be a valid way of testing your hypotheses. Okay, so hopefully that shows that you can easily compare different thermodynamic models for fractional crystallization. You can dig into the oxide differences in the liquid, and then you can also dig into the differences in the phase abundances and the phase chemistry to understand why there are these differences in liquid chemistry. Okay, see you soon for some more videos.